And there is a gray zone called radiating near field, the Fresnel region. That is sort of in between. Sometimes we can approximate far field conditions, but then after the far field region, or the so-called Fraunhofer region, they can approximate the field as a transverse electromagnetic field, TEM. So rule of the thumb, radii of these regions are 1 is this 0.62 square root d to the power 3 divided by lambda, lambda being the wavelength. D is the largest dimension of the antenna. And then the second radius is R2 is 2d squared divided by lambda. So it depends not only lambda, but the size of the antenna, the dimensions of the antenna. Larger antennas would have fairly long near field regions. So this is important when we design things like metasurfaces for antennas. Often, if you try to steer the beam of an antenna, very large antenna, your metasurface is pretty much in the near field, not in the far field, but we have to approximate some far field conditions. We will get to that later when we get to the last stages of this course. I'm covering all these things now because I will be talking about near field phase transformation, far field approximation. So if you are not familiar with this, you may not understand some of the things later. Although these things look very basic, as I said before, most of you who has been doing research in RF or antennas or micros probably know already these things. This is only for the few who did not come across. Okay, then more basics, isotropic antenna. What is an isotropic antenna? It's an antenna that radiates uniformly in all directions. It radiates equally in all directions. So the radiation pattern of an isotropic antenna is what? A sphere, right? A sphere. And normally we don't need antennas like that most of the time. If you want one, it's very difficult to make one like that has a perfectly sphere. It is not impossible, but it's difficult. So this is mostly hypothetical. But that is quite important because the directivity of the other antennas are defined relative to this hypothetical isotropic antenna. So almost all antennas are directional. It's an antenna having a property of radiating or receiving electromagnetic waves more effectively in some directions than in others, like this one. This will radiate better in this direction when you use it as a transmitting antenna. It radiates most of the energy in this direction, not much in the transverse directions, little bit in the other directions. Also, there's something called reciprocity in electromagnetics. That means most of the antennas are reciprocal. That means it will also receive signals better in this direction. In other words, the signals you see coming in this direction are received well, whereas waves coming in this direction are received well. Electromagnetic waves incident in other directions, like on the XY plane, on this plane, are not received very well due to reciprocity. Then, what is an omnidirectional antenna? The omnidirectional antenna would radiate the same on one plane. So the radiation pattern, 3D radiation pattern of a omnidirectional antenna could be something like a toroid here. When we do a pattern cut on XY plane, the radiation pattern becomes a circle. So if you take this donut, right, or a toroid and cut it in the middle on XY plane, what you get is a circle. And that is your radiation pattern on XY plane. And so on that plane, it receives all the waves equally in all directions, and also it transmits waves on that plane equally in all directions. That's the meaning of omnidirectional. But if you take a pattern cut on another plane, for example, YZ plane or XZ plane, cut this donut in those planes, you get something like this. So it is not omnidirectional on that plane. But they are useful because, for example, if you're communicating on the ground, think about transmitting antenna for television, right? Television tower. The tower antenna, it doesn't need to transmit upwards. Most of the subscribers, TV antennas in houses, etc., are on more or less on the same plane. So but it wants to cover the whole neighborhood, want to transmit to the whole neighborhood on more or less the same elevation. So this kind of antennas are useful for some transmission equipment, such as television transmitting towers. Now we get to numbers, qualitatively assess. How you measure the directivity of an antenna? Qualitatively, how you define it? Directivity, sometimes also called maximum directivity, is the ratio of maximum radiation intensity to the average radiation intensity. Okay, that's not very clear. The maximum radiation intensity is obvious, right? So for this antenna, suppose you input some power into it, 10 watts, and it radiates bits in this direction. So you measure power density in that direction. That is the maximum power density. So that is U max. That is U max. But what is the average power density? The average power density, or radiation density is defined as intensity produced by an isotopic radiator radiating the same amount of power. So now you take the same amount of power, PT, which is 10 watts in our example, and apply it to isotopic radiator that radiates that power in all directions equally. So power density in a particular direction is U naught, radiated power divided by the surface of the sphere. So when you substitute those, you get this equation for maximum directivity in terms of the maximum radiation density and radiated power. And U max here is sorry. So that is the then you can also, if you want, you can calculate the total power radiated by any antenna by integrating the radiation intensity using this equation. So I will not try to explain all these equations. If you want to understand these or derivations, you can find in textbooks like Balanis. I think some of these things I got from Balanis, but there are several very good textbooks explaining how these are derived. This is just a exercise for you. Whenever you don't have to do it now. For example, if you have an antenna that's radiation, that is an omnidirectional antenna, and its radiation intensity is given by this equation, you can see that it does not depend on phi, it depends only in theta. These are the two angles in the spherical coordinates. So that means an omnidirectional antenna, like the one you see here. When you plot it against phi, it is a circle. When you plot it against theta, it's more like some sort of a donut. So you have analytical expression for this antenna, and you want to find the maximum power radiated by this antenna. When you know the radiation intensity analytically, even if it is approximate, simply substitute this in this equation. U theta phi is this, U max sine theta, and integrate to the double integration with respect to theta and phi. Theta changes from 0 to phi and 0 to pi, and phi changes from 0 to 2 pi, sorry. Why is that? That is to cover the whole sphere. So this is the angle theta. To cover upper and lower hemisphere, theta should go from here, theta equals 0, all the way down to here, that is theta equals pi, or 180 degrees, right? And then you have to cover all angles of phi. So we start from here, x-axis, which is phi equals 0, and you go the full circle, come back to here. So phi goes from 0 to 360 degrees, or 2 pi in radians. That's the reason the theta integration range goes from 0 to pi, 180 degrees, and phi integration is from 0 to 2 pi. So in this one,
Hello, sir. Your voice is not coming.
thank you.
Okay.
But, it happens automatically. Maybe this some wire is loose.
Okay. No issue,
Okay,
sir.
now it is okay, right?
Yes, sir. All right.
Okay, so substitute that in this equation. PR is 5 cos U max, and you get the directivity of this antenna, which is 1.27. This is in linear scale, directivity of 1.27. Pretty much all antennas should have directivity greater than 1, because what is the directivity of isotropic radiator? Isotropic radiator has the lowest directivity, that is equal to 1. So all other antennas are directive, and their directivity is greater than 1 in linear scale. When you express directivity in log scale in dB, so we take log 10 of this 1.27, and then multiply that by 10. That's how we express in dB, like in normal electrical engineering for power ratios. not 20 log, that's 10 log, because this is sort of a power ratio, right? All these we are power densities. So that becomes 1.04 in dB. That is the directivity of this antenna in dB. We normally write it as dBi. That is because this is the directivity relative to an isotropic radiator. Right? Always remember to express properly, that's the directivity in dB relative to isotropic radiators, 1.04 dBi, or in linear scale is 1.27. So isotropic radiator has a linear scale, linear gain of 1 and decibel gain of 0 dBi. That is the reference. That is the hypothetical isotropic radiator. All the other antennas should have directivity greater than 1 in linear scale or greater than 0 dBi in decibels. Now there's another parameter that's very much related to directivity, that is gain. So gain comes on top of directivity. It's usually related to directivity. It's directivity times another factor K, which is the radiation efficiency, and that K accounts for losses in the antenna, ohmic losses, dielectric losses, all sort of dissipation, and so on. So if it is the antenna is totally lossless, efficiency is equal to 1, gain is equal to directivity. But that is a very ideal case. In practice, nothing is ideal. So there are losses. Therefore, gain is a little bit less than directivity usually. Another important parameter or aspect of antenna design is matching. This is very similar to impedance matching in transmission lines, in guided waves, in radio frequency transmission lines, microwave, waveguides, etc. So even those who have done RF, not done any antenna work, probably know this part. Impedance is a complex number, as you know. Impedance is resistance plus J times reactance. In antennas, input impedance is a function of frequency usually. So all these are frequency dependent. So when we connect an antenna to a transmission line, or pretty much anything to a transmission line for maximum power transfer, the resistance, the antenna resistance should be equal to transmission line characteristic impedance. And the antenna reactance should be 0. This is the condition for perfect matching. So we call the antenna is perfectly matched to this lossless transmission line. In reality, antennas that's different because the resistance and reactance both varies with frequency. So it's almost impossible to match perfectly at all the frequencies you want the device to operate or the antenna to operate. So at least at some frequencies, the resistance, antenna resistance is not equal to transmission line characteristic impedance, and antenna resistance is not equal to 0. So perfect matching is impossible over a range of frequencies. It may be possible at one frequency, but it's for few discrete frequencies, but not possible in practice over a very large range of frequencies. But reasonable good matching is possible. Not perfect matching, but good matching is possible. So we need a way of quantitatively expressing again the matching, and that is used in terms like return loss or VSWR, voltage standing wave ratio, the same in transmission line theory, and return loss. So I will not go through this right? I believe all of you are familiar with transmission line theory, right? Do I need to go through this? We can just explain the.
Audience can respond.
Sorry? Yeah. What do you think, audience? Anyone wants me to go through this? I will go, even for one person.
I think you can go briefly and
Okay, go briefly, right? Because you can find all these things in RF handbooks, RF textbooks. I will go very quickly. So in general, in a transmission line, right, there's incident wave and a reflected wave. And in general, because you have a transmission line that has a characteristic impedance, usually Z0 is the characteristic impedance of the transmission line. If it is a lossless transmission line, that is real. And then we terminate the transmission line by a load, and load impedance is ZL, which is in general complex number. So if we terminate the transmission line by an antenna, ZL is the antenna impedance. So when the antenna is not matched perfectly to the transmission line, when you apply a wave to the transmission line, that means you created the incident wave, incident voltage Vi, and part of that is reflected by the antenna, and that is the reflected wave VR. So we have two waves in the transmission line, reflected wave and the incident wave. So this ratio is called the reflection coefficient. Both of them are complex in general, so this is also a complex number. And you can define this along the transmission line. So it's a function of x. X is the length along the transmission line. So that's basically comes from the transmission line theory. And so this can be expressed by a reflection coefficient, rho. Rho is the magnitude of the reflection coefficient, and an angle phi. This magnitude of the reflection coefficient, that's a ratio between these two, is quite important, because that defines, that is a way to define the mismatch in the transmission line.
again, sir, you are not audible.
Yeah, it is becoming habit. Let me move the mic a little bit away, because
Now
I
it's
have
perfect.
two cables, one for the mouse and one for. So the maximum voltage along the transmission line is incident voltage times 1 plus rho, and the minimum voltage is 1 minus rho. In fact, if you can measure the voltage along the transmission line, you see this variation along the length x. So the ratio between maximum voltage and minimum voltage is called VSWR, voltage standing wave ratio. Voltage standing wave ratio, Vmax divided by Vmin, and that is equal 1 plus rho divided by 1 minus rho. Okay, so this is one of the measure of mismatch, VSWR. So if you have equipment to measure VSWR, you can actually measure it. And then you can determine reflection coefficient gamma by rewriting this equation like this. Reflection coefficient is VSW minus 1 divided by VSW plus 1. When I was doing my undergraduate RF courses, we had an experiment called slotted line, and we were actually measuring the voltage wave standing ratio. We were measuring the voltage along a slotted transmission line. Do you do it in your labs these days?
Yes, we have been.
Yeah. So that is so when you, that is basically what I'm saying. You have seen this, right? V max and V min. If you have a next time when you do the experiment, you can see it. And from that, you can calculate this. And then from that, you can calculate the reflection coefficient. Now, one thing I forgot to mention is you can also calculate reflection coefficient if you know. So this gamma L is actually these two are equal. The load reflection coefficient gamma L. So this is the complex number. Take the amplitude of this complex number, that is rho. So if you know the transmission line characteristic impedance, and you know the load impedance, that is the antenna impedance, using this formula, you can calculate gamma L, that is a complex number. Take the magnitude of that, that is rho. That's how we normally calculate it. Now, another parameter representing the same thing, VSWR, is by return loss. So return loss is reflection coefficient magnitude square. That's the same as this. This is real, right? This is the reflection coefficient magnitude, and return loss is reflection coefficient square of that. That is in linear scale, but normally we write it in dB again. So when we write it in dB, it is minus 20 log base 10 of this. Or it's minus 10 log rho squared, like minus 10 log base 10 rho squared, because because 10 log square becomes 20 log 10 log rho square becomes 20 log rho, so it's minus 20 log rho. One mistake a lot of students do is writing return loss as a negative number in dB. That is incorrect. Return loss is positive because this is less than 1. The log of that is negative. With this negative sign, return loss is positive. For example, return loss of an antenna could be 10 dB, 20 dB at a given frequency. But if you write the reflection coefficient magnitude, rho, in dB, like in scattering parameters, you can write this also in dB, then it becomes negative. So when you write, be careful. If you say the input reflection coefficient magnitude of this my antenna is minus 10 dB, that is correct. But if you're talking about return loss, then you say the return loss of this my antenna is plus 10 dB. Okay. The other things are standard transmission line theory. When the load impedance is equal to characteristic impedance of the line, it's a perfect match. Then rho is equal to 0. Substitute those values. Rho becomes 0. And when rho becomes 0, VSWR becomes 1, and so on. But those are the ideal conditions. That means there's no reflected wave. There's only one wave in the transmission line. That's the incident wave. Whole energy in the incident wave is absorbed by the load. or radiated by the antenna if it is an antenna. So there's no reflection. In that case, the return loss is minus infinity dB. Sorry, return loss is plus infinity dB. And S11 is minus infinity dB. Another parameter sometimes mentioned, it's actually useful when you calculate the power budgets, that is the mismatch loss. Because of this mismatch, the transmission through your, for example, in the wireless transmission line system, experience a loss, and that can also be calculated if you know rho. So in linear scale, it's 1 minus rho squared. In decibels, minus 10 log to the base 10, 1 minus rho squared. Okay, so that is the transmission line side of this. Now the other important parameter is bandwidth, because normally we don't design antennas to operate at one frequency. We need the antenna to operate over range of frequencies, whether it is a wireless communication application or the radar application. Your signal has a finite bandwidth. Your radio frequency waves would have finite bandwidth. So you need the antenna to operate well over the entire bandwidth of your system. So that means the antenna gain should be good over that bandwidth. There's a lot of things actually when you say antenna bandwidth, it's not just one thing. Gain should be good over the whole frequency range. Radiation pattern should be good enough for the whole range, and matching, that is VSWR or return loss or mismatch loss, one of those is enough to define matching. You don't need all three, right? One of these will do, and that should be good. So because of this, people define things like 10 dB return loss bandwidth. That is the bandwidth within which your antenna has a return loss greater than 10 dB. Return loss greater than 10 dB in that frequency range. And that's almost equal to 2 into 1 VSWR bandwidth. That exact meaning is your antenna, when it is connected to the design transmission line, the voltage standing wave ratio is less than or equal to 2. When it is less than or equal to 2, that is another way to define match bandwidth. So both of these are ways of defining the matching bandwidth of matching, but the gain bandwidth is completely different. The way we define gain bandwidth is you mention particular gain variation. For example, 3 dB gain bandwidth means the gain does not change by more than 3 dB within this bandwidth. Suppose the maximum gain is 10 dBi, then within this 3 dB gain bandwidth, the gain of the antenna is always greater than 10 minus 3, that is 7 dBi. Right? That is the 3 dB gain bandwidth. Likewise, you can define 3 dB directivity bandwidth, etc. Radiation pattern is difficult to define because its nature is not just one number, but you should be careful about variation of radiation pattern in some applications. Now power, right? Almost always we use the antenna as a part of a system, a communication system or any other. So we transmit certain amount of power and we want to know, we need to determine what is the received power. And if you are transmitting PT watts, what is the power received by the receiving antenna? This is transmitting antenna, we're transmitting PT watts, and this is the receiver antenna, what is the power received by the receiving antenna? And the distance between the two is R, and we assume that this antenna is in the far field of this antenna and so on. So under far field conditions, it's quite easy to calculate the power received by the received antenna. All you need, this is the way to derive it. I will only explain the equations. This is the power transmitted by the transmitting antenna, right? PT. And what is the power density at the receiver antenna? The distance between the two is R. So for a moment, assume that the transmitting antenna is isotropic radiator, right? Isotropic radiator, not a directive antenna. And we are transmitting PT watts. And that PT watts would go equal in all directions. So at the receive antenna, power density is PT, power density measured by watts per meter squared is PT divided by the area of this big sphere, right? Big sphere with the radius R. So area of a sphere with the radius R is 4 pi R squared. So power density at the receiver is PT divided by 4 pi R squared. That is the case if you have an isotropic radiator. But now we have a directive antenna with the gain of GT. So because of this antenna gain, because it's directing power more towards this and less in the other direction, it's better than an isotropic radiator. So the received power becomes PT times that. Sorry, GT. GT is the gain of the transmitting antenna, GT times that. So the power density here becomes PT GT divided by 4 pi R squared. So that is the power density. But we need the received power, right, in watts, accepted by the receiving antenna. It turned off again, right? I'm not sure why it is. Is it on now? Can you hear it?
Yes.
Yeah, it's fair because the mic is connected. This mic is not disconnecting. But anyway, if that happens, give me a shout again.
Yes. Yes.
So there's a theory that says the received antenna behaves like a bucket of collecting. That's a simple explanation. The receiving antenna is like a bucket that collects electromagnetic intensity or power. And the area of this bucket, that's called effective aperture of a receive antenna, is the gain of the receive antenna. That's the same gain even if you use it to transmit, times lambda squared, the wavelength squared divided by 4 pi. So this is sort of the effective area of the receive antenna. So we get this many watts per square meters of radiation, and receive antenna will collection area of this many square meters. This is in square meters. So the collected power PT would be this times that. P times effective area. So PT, GT, dr lambda squared divided by 4 pi r squared. And that is the case ideally under ideal propagation conditions. But in practice, there are other issues. For example, the clouds and or vapor and other things absorb electromagnetic power. So there's a propagation loss. So we need to include the propagation loss in this equation. But this is a very important equation to calculate power budget, etc. in almost all wireless systems, whether it is an IoT system or communication system, any wireless communication system or a radar system. And I will not go through this example, but if you want, you can take a snapshot and do this as a homework. That's to calculate, just to get yourself familiarized with the calculation of the received power. Yeah, take a snapshot or a photo, and it's simple substitution, except that we have to convert everything into proper units, right? And if you use this equation, the gain values should be linear gain, not decibels. Everything should be in metric. But there's a decibel equation. You can write the whole equation in decibels as well. Then multiplication becomes summation. Because in dB, when you convert to log, multiplication becomes summation. So there's a decibel version of the same equation, but if you're using this as is, you need to convert these gain values to linear values and substitute. So I already mentioned this one, direct-to-the example, right? Okay, no, maybe not. This is another example if you want to do a practice exercise. This is a radiation pattern of an antenna. I believe this is different to the one I did before. This one, radiation pattern is U max sine theta. Similarly, if the radiation pattern is given by U equals U max cos theta, you can substitute that, do the analytical integration, and find the directivity. Now, about antennas, I have quite a few of these basic antennas and like dipoles, and then more complicated antennas. Is it worth going through little simple ones like dipoles and loops quickly before we get to, I think the photos are not that important. So the dipole type antennas are very basic. And there's a history of that. Actually, there's an evolution of this. And this is a transmission line, right? It's a two-wire transmission line, like those two-wire lines we used to have to connect TV antennas, Yagi-Uda arrays in rooftops to our TV sets. They're becoming increasingly redundant. They may still be used in some areas of the world. The twin line transmission line. if you open the transmission line at one end, just open here, it does not radiate very well, right? It's an open circuit, so it might radiate just a little bit, but not a good antenna. It's a pretty lousy antenna. However, if you open up the two wires to the shape like this, like a little bit like a horn, then it starts radiating. Then it becomes an antenna. Now to radiate it very better, normally we make these parts vertical, bend by 90 degrees, make this part vertical up, make this part vertical down. Then we have something called a dipole. So the transmission line, this is the upper section, the wire or a thin conductor, and this is the lower conductor. And this is the current distribution of a dipole. So it is zero at the ends because current got to be zero, and it increases toward the center. When the length of the dipole is half wavelength, lambda divided by 2, that is from here to here, then the current in the middle becomes maximum. The half wave dipole is a very useful antenna, extremely basic but very useful for several reasons. One is its impedance. At its resonant frequency, its resistance, its impedance is resistive. That means reactance is zero. And the resistance is around 70, 73, 75, which is very good because you can match it to some transmission lines with simple ways. Now, if the length is not lambda naught by 2, it is larger, then you can have lambda dipole, 2 lambda dipole, etc. These are not very popular. And also you could have smaller dipoles, much smaller, quarter wave dipole, etc. But the half wave dipole is the most popular one. And these are the radiation patterns. This is a half wave dipole radiation pattern. This is a 1 wavelength dipole radiation pattern, which is narrower, so it has better directivity. When we make it even longer, this one is 1.5 lambda dipole, then it becomes very messy, multiple beams, etc. Not useful for a lot of application. Another is a monopole. Monopole is half of a dipole. So you suppose you cut this across this plane and put a conductor on this plane, very good conducting sheet. That conducting sheet would create an image of this half of the dipole, which is a monopole. This part is a monopole. It will create this image, and it will behave very similar to a dipole. So with half the size, you still have an antenna that is reasonably good, but it needs this ground plane, conducting ground plane. But it's useful in some tall antennas, especially at lower frequencies. The dipoles are very tall, and you can use the ground as a conducting plane, the ground plane. In fact, you can put extra conducting material, mesh or sheets in the ground to create a better ground, and that way you can make a good transmitting antenna at low frequencies that is only half the height of a dipole. For some antennas, like these tall ones that can be make a monopole. Okay, so and the other simplest antenna is a loop. Okay, now this is more about half wave dipole. Same thing. This is quarter wavelength. This is quarter wavelength. Input impedance is almost resistive. Input resistance is 73 ohms. Input reactance is almost 0. I already mentioned all these things, right? Radiation pattern, omnidirectional on the horizontal plane. If the antenna is vertical, this is from another good book on antennas by Connor. So it's omnidirectional antenna on the horizontal plane. The radiation pattern is circle. In the vertical pattern cut, it has directivity, and that radiation pattern can be approximated by these equations. D theta, that's the electric field, radiated electric field. And this is the power density, radiated power density, all normalized. Power density is proportional to square of the electric field. As you can see, they only depend on theta, does not depend on phi because it's omnidirectional. And the power density is maximal on theta equals 90. That is this direction on this plane. Theta equals 90, that's the horizontal plane. And when you substitute these things in that equation, the linear directivity of a dipole becomes 1.64. Or in decibels, it is 2.16 dBi. 2.16 dBi. I should be here. For a short dipole, it could be less, something like 1.26 dBi. Okay, the dual of a dipole is a loop. Because if you make a dipole very, very small, very small, this length, not lambda by 2, as I said, you can make it very, very small. What you get is infinitely small, almost no length dipole. So that is like the smallest electric dipole. Likewise, you can create a magnetic dipole, and that is a very small loop. But in practice, very small loops don't radiate very well. So usual loop antennas are made out of, again, conductors with circulating currents. Of course, you have to feed it somewhere, so you have to cut this loop and connect it to a transmission line. So circular loops, square loops have radiation patterns that are similar to a dipole when the loop is very small. This is a very small loop, like the diameter is lambda divided by 10. Not a very efficient antenna. When the loop becomes larger, this is a loop with the diameter of lambda. It has more complex radiation patterns, and when the loop becomes very large, like 5 lambda, get a lot of lobes, multiple lobes. But a loop is another popular basic antenna. So this is a summary of those straight conductors, small and large loops. And then another common antenna is called helix. You probably have seen these things, right? It has a helical conductor and usually a ground plane, and it's connected to a transmission line here. For example, if you're using a coaxial transmission line, The inner conductor of the transmission line is connected to this helix, and the outer conductor is connected to a small ground plane. When the helix height is small and the pitch is small, it radiates more like a dipole radiation pattern. But when the pitch is long and the helix is long, the radiation is going upwards. So this is called an end-fire helix. These are more like broadside helix. Okay, these are some of the historical. Okay.
Sir,
Yeah.
your voice is not coming.
So in the next spec, I might, I don't know, I will disconnect it and reconnect or do something. Maybe I will rejoin. It's getting annoying now. Okay, so very tall radio mass transmitting 2 megawatts across the Europe, and it was the world's tallest structure until it collapsed in 1991. It's now there. A massive horn in Bell Telephone Labs, Bell Labs in New Jersey, in USA. And this is to discover cosmic microwave background radiation from space. So you need very large collection area, massive horn. Some of very interesting massive antennas. This is Arecibo radio telescope. It's actually dug in the ground. It's a dish, parabolic dish in the ground with the sub reflectors and the collectors here, feeds, etc. I forget. It's in South America, I believe, and that's 300 meter in diameter, and some historic Hudson's with the Marconi's Spark Gap transmitter. This is Marconi's wireless station in Massachusetts, USA, and some of the Marconi's experiments, etc. So I think the time to get the next break, right? When we come back, this is what we are going to do. We will go. So these are like what we have done now is very, very basic antennas. Now in the next lecture, we will dig into more details about specific types of antennas. These are not all the type of antennas. I just pick some selected antennas that are either very common or useful but not very popular. And I have papers and slides on some of these, so I will shift to those and try to explain, especially those marked in red. I will try to explain a little bit more details. So that is the plan for the next lecture. And then I will not be teaching tomorrow, as you know. Chandra and Saurabh, I think, giving 2 lectures tomorrow. I have to attend few functions. IEEE president is coming to Sydney and our university, so I have to attend the dinner and some daytime events with the president of IEEE from USA and also Region 10 director in Asia Pacific director. So going to be a very busy day. But when I come back Wednesday, we will look into these electromagnetic surfaces, and that are some of these inspiring, um, and they will come up in future lectures. So when we go into resonant cavity antennas, um, and near field metasteering, this knowledge will be useful. Okay, so let's take a break of,
Okay.
I forget the time we have.
Okay. Thank you, sir, for your interactive this session. And now we'll resume this next session at 2 p.m. So,
Yeah, that's 2 p.m., right? Okay,
and
see you.
this is for India, and for Sydney, this is 7:30 p.m.
Yeah, 7:30.
Yes.
Okay, so about 45 minutes.
Yes. So,
Okay, see you then. I will see, I'll disconnect and join again and see whether
yes.
it will help.
Okay.
Okay, thank you. Bye-bye.
Bye bye. Okay. So, audience, please join at 2 p.m. I will resume this.